Atoms. Atoms are zero point 0.1 nanometers wide. That is 10 to the minus 10 meters. They are simply too small to see under a microscope. Yet, they contain protons and electrons. At the center of the atom lies the nucleus. Its radius is 10 to the minus 14 meters, just 1/10,000th the size of the atom itself. It holds the protons and the neutrons. Because of the protons, the nucleus carries a positive charge, and it holds almost all of the atom's mass. Meanwhile, electrons orbit that nucleus in shells, or energy levels. They carry a negative charge, and their mass is negligible. However, their orbital volume defines the atom's actual size. Let's break down the particles. Protons have a mass of 1 and a charge of +1. Neutrons also have a mass of 1 and 0 charge, as the name suggests, neutron sounding like neutral. Electrons have practically 0 mass and a charge of -1. By nature, atoms have no net charge, that is, no overall charge. Their protons and electrons are exactly equal in amounts, so the opposite charges cancel out. But if those numbers are unequal, you have an ion, an atom or group that has gained or lost electrons to create a net charge. For example, an ion simply has 2 extra electrons compared to its protons. Finally, let's think about the nuclear symbol. Take sodium. Its mass number is 23 and its atomic number is 11. The atomic number is your proton count. The mass number is protons plus neutrons. To find the number of neutrons, just subtract the atomic number from the mass number. Next, elements. An element is a substance where every atom has the same number of protons. There are exactly 118 known elements. Ultimately, it is the proton count that determines the atom type. 1 proton, you have hydrogen. 2 protons, you have helium. 6 protons, you have carbon. We identify these elements with symbols. Many are intuitive: C for carbon, O for oxygen, or Mg for magnesium, but others are completely non-obvious, like Na for sodium from earlier, or Fe for iron, and Pb for lead. They're not random, however, and they do have an origin if you trace it back. For example, Pb sounds like plumbing, which is a clue. Next, we have isotopes. These are atoms of the same element with the same number of protons, but a different number of neutrons. That means they share the same atomic number, but have different mass numbers. And just to review, to find the neutrons, simply subtract the atomic number from the mass number. Let's look at an example. Take carbon-12 and carbon-13. They both have 6 protons and 6 electrons. However, carbon-12 has 6 neutrons, while carbon-13 has 7. Now, because elements exist as multiple isotopes, we use something called the relative atomic mass, or AR, instead of a single mass number. This is a kind of weighted average across all of an element's isotopes based on their natural abundance. Think of how we say that the average family has 2.3 children. There's no actual family that has 2.3 children, but we're able to make sense of this. To calculate the relative atomic mass, you find the sum of each isotope's abundance multiplied by its mass number and divide that by the sum of all the abundances. Here is how that works for chlorine, which we'll see listed with a mass of 35.5 on the periodic table. If we look at its natural abundance, 75% or 3/4 of chlorine is chlorine 35, and 25% or 1/4 is chlorine 37. To find the average, multiply 75 by 35, then 25 by 37. Add those totals together to get 3,550. Divide that entire sum by 100, and you get chlorine's exact relative atomic mass, 35.5. Next, compounds. A compound is formed when 2 or more elements are chemically bonded in fixed proportions. Because these bonds are chemical, it's difficult. Doing so requires an entirely new chemical reaction. And remember, bonding only ever involves the electrons on the outside. The actual nuclei on the inside remain completely unaffected. There are 2 primary types of bonding. First is ionic bonding, which occurs between a metal and a non-metal. Sodium chloride is the go-to example here. The metal loses electrons to become a positive. There are 2 primary types of bonding. First is ionic bonding, which occurs between a metal and a non-metal. The metal loses electrons to become a positive ion, while the non-metal gains them to become a negative ion. These opposite charges attract each other powerfully. You see this in compounds like sodium chloride, magnesium oxide, and calcium oxide. Considering sodium chloride as your go-to example, the metal in that case is sodium and the non-metal is chlorine. Therefore, sodium would lose an electron while chlorine would gain an electron, and the 2 ions would be attracted to each other. The second type of bonding we have is covalent bonding. This happens between 2 non-metals. Instead of trading electrons, covalent atoms share them. Examples here include hydrogen chloride, carbon monoxide, and of course, water. The compound differ entirely from its constituent elements. Consider iron. Iron is lustrous and magnetic. And also consider sulfur, a grey solid. Bond them together, that should say yellow, a yellow solid. Bond them together into iron sulfide and you get a dull grey solid that retains neither of the original properties. We represent these compounds using chemical formulas. These use element symbols to show the exact ratio of atoms. A small subscript number tells you the amount of that specific element. And if you see brackets, the number directly outside multiplies everything inside. Most famously, H2O comprises 2 hydrogen atoms for every oxygen atom. For instance, the formula for calcium hydroxide is Ca, then OH in brackets, followed by a 2. That translates to 1 calcium, but 2 oxygen and 2 hydrogen. Finally, let's walk through some common formulas so their structures become second nature. As said earlier, H2O is of course water. CO2 with 1 part carbon and 2 parts oxygen is carbon dioxide. Notice the di meaning 2. Whereas CO with just 1 of each is carbon monoxide, mono meaning 1. NH3 brings together 1 nitrogen and 3 hydrogens to make ammonia. HCl, pairing hydrogen and chlorine, is hydrochloric acid. More about them later. For the salts, NaCl is sodium chlorine, which gives you the standard, for the salts, NaCl, sodium and chlorine, gives you the standard sodium chloride. Swap the sodium for a calcium with 2 chlorines, and CaCl2 is calcium chloride. And lastly, the heavier compounds. H2SO4, 2 hydrogens, 1 sulfur and 4 oxygens, is sulfuric acid. And Na2CO3 with 2 sodiums, 1 carbon and 3 oxygens, well, that's sodium carbonate. Now let's talk about chemical equations. When tracking chemical reactions, we use equations. The simplest form is a word equation. It is easy to read but slow to write, and it completely hides how the actual atoms are changing. You simply write the reactants on the left, draw an arrow pointing to the products on the right, and you're done. For example, methane plus oxygen yields carbon dioxide and water. To see the actual chemistry, though, we use symbol equations. Instead of names, we use exact chemical formulas, like writing 2Mg plus O2 yields 2MgO. But notice the numbers there. In a reaction, atoms cannot just appear or disappear. The number of atoms for each element must be exactly equal on both sides. We call this balancing. To balance an equation, you can only do one thing: add coefficients. These are large numbers placed directly in front of a formula. You must never change the small subscript numbers within the formulas themselves. For example, if you see H2O, you are not permitted to change the 2 in H2O. Sulfuric acid is always H2SO4. If you change those tiny numbers, you change the chemical entirely. So, here is the method. Step 1. find an unbalanced element and trial a coefficient to fix it. Step 2. Check the knock-on effects, because adjusting one element often unbalances another, like when solving a Rubik's Cube. Step 3. Repeat this process until every element matches. Here's a pretty complicated example we're going to walk through. On the left, we have H2SO4 and NaOH. That's sulfuric acid and sodium hydroxide. On the right, we have Na2SO4 and H2O. So step 1 says, look at the right side. We are short on hydrogen. So we place the 2 H2O. Following step 2, we need to check the knock-on effect. Because we put a 2 in front of H2O, we now have an excess of hydrogen and oxygen on the right. To fix this, we look back to the left and place a 2 in front of the NaOH. Then step 3, verify. Because we added that 2 on the left, the sodium, the Na, has successfully corrected itself. Finally, do a tally of the elements just to make sure you got it right. Now let's talk about mixtures. Unlike compounds, the parts of a mixture have absolutely no chemical bonds between them. These parts can be individual elements or entire compounds. If you had a magic pair of tweezers, you could separate the parts of a mixture particle by particle. This cannot be done with water, for example. Because nothing changes chemically, the final properties are just a blend of the original parts. For example, if you mix iron powder with sulfur powder, you will still clearly see the yellow sulfur and the iron will remain completely magnetic. Because these parts are not bonded, we can pull them apart using purely physical separation methods. Such methods include filtration, crystallization, simple distillation, fractional distillation, and even chromatography. You add gas, oxygen gas, carbon dioxide gas, and argon gas in small amounts. Or, to give you their chemical symbols, N2, O2, CO2, and then argon. Crude oil, the oil we dig up out of the ground, is simply a mixture of varying hydrocarbon molecules. So let's now zoom in on paper chromatography. We use this specific method to separate the different dyes or substances within a liquid mixture like ink. Here is exactly how you do it. Step 1. Draw a baseline near the bottom of a piece of filter paper. You must use pencil for this line because pencil is insoluble and will not interfere with the experiment. Step 2. Place a spot of your ink directly onto that baseline. Next, place the paper into a beaker containing a solvent such as water or ethanol. Crucially, your ink spot must not touch the solvent directly. Fourth, put a lid on the beaker. This prevents your solvent from evaporating. The solvent will naturally wick up the filter paper, carrying the dyes upward with it. Because each dye travels at a remarkably different rate, they begin to separate out. You will see one distinct spot for every soluble dye. Any insoluble dyes will simply remain stuck down on the baseline. Once the solvent nears the very top of the paper, remove it and leave it to dry. And then finally, you have a chromatogram, a clear, readable pattern of separated spots. But we're not done with separation techniques yet. Let's now have a look at filtration. This separates insoluble solids from liquids. You use it for two main reasons. Either to isolate a solid product that you want to keep, or to strip away solid impurities that you need to discard. But what if a solid is soluble, meaning it has dissolved into the liquid, like sugar into water? For that, we have two different methods. Method one is evaporation. You pour your solution into an evaporating dish and apply heat. As the solvent evaporates, crystals begin to form. You keep heating it until the solid is completely dry. However, there is a catch. This method only works if your salt does not decompose under intense heat. If your salt is sensitive to heat, you must use method 2, which is crystallization. Here, you heat the solution gently, just concentrate it. The moment you reach the point of crystallization, you remove the heat entirely and let it cool down. Because the salt becomes insoluble when the liquid is cold and concentrated, it will naturally crystallize out. From there, you simply filter the crystals and leave them to dry in a warm place, a drying oven or a desiccator. Let's put this into practice with rock salt, which is simply a mixture of salt and sand. The trick here is to exploit their key physical difference. Salt dissolves in water, but sand does not. Here's the process. First, grind the mixture down. Smaller crystals dissolve much faster. Next, add water and stir thoroughly. The salt will dissolve into the water while the sand remains exactly as it is. Now, filter the mixture. The solid sand gets trapped in the filter paper while the liquid salt solution passes straight through. And finally, take that pass-through solution and evaporate the water away. What you are left with is pure dry salt crystals. Next, we have distillation. We use simple distillation to separate a liquid from a solution. You heat the mixture and the component with the lowest boiling point evaporates first. That vapor cools, condenses, and is successfully collected while the remaining solution stays behind in the flask. Think of extracting pure water from seawater where the solid salt is left behind. However, there is a catch. This only works if the substances have significantly different boiling points. If their boiling points are too similar, the liquids will simply remix. In that scenario, you must use what's called fractional distillation. Fractional distillation separates a mixture of multiple liquids. This is exactly the process used to refine crude oil. You place the mixture in a flask, attach a fractionating column to the top, and apply heat. Because each liquid has its own specific boiling point, they evaporate at different times. The liquid with the lowest boiling point rises to the top first where it is condensed and collected. Now, liquids with higher boiling points may also begin to evaporate, but because the fractionating column is naturally cooler at the top, those heavier vapors condense part way up and simply run right back down into the flask. Once that first liquid is collected, you progressively raise the temperature. This allows you to boil off and collect each subsequent liquid one clear fraction at a time. Let's now change gears and talk about the history of the atom. In the early 1800s, John Dalton proposed that atoms were simply solid spheres and that different spheres made up different elements. But by 1897, J.J. Thomson proved him wrong. Thomson's experiments revealed smaller negative particles, which we now know as electrons. This completely replaced the solid sphere with what was called the plum pudding model. Picture the atom as a general ball of positive charge with negative electrons randomly embedded inside it. Then came 1909. Ernest Rutherford and Ernest Marsden conducted the famous alpha particle scattering experiment. They fired positively charged alpha particles, which are helium nuclei, essentially, at an impossibly thin sheet of gold. If the plum pudding model were accurate, those particles should have passed straight through, or only deflected slightly. But that is not what happened. While most did pass straight through, some deflected at incredibly sharp angles, and a few, just a few, deflected straight backwards. The conclusion was undeniable. The plum pudding model was dead. In its place, Rutherford proposed the nuclear model. A tiny, dense, positively charged nucleus at the exact center, surrounded by a cloud of electrons, with the vast majority of the atom being entirely empty space. But there was a flaw. A free-floating electron cloud would eventually be attracted to the positive nucleus and collapse inward. So, Niels Bohr stepped in. He proposed that electrons do not just float, they orbit the nucleus in fixed shells at fixed distances. This was supported by later experiments and explained a great deal of what chemists were observing. The final pieces fell into place soon after. About 1919, Rutherford formally identified the positive particles in the nucleus and named them protons. Finally, in 1932, James Chadwick discovered the evidence for neutral particles in the nucleus, now known as neutrons. And with that, our modern nuclear model was essentially complete. So now, let's look at the electronic structure. That is, how electrons are actually arranged in an atom. Electrons live in energy levels, which we call shells, and there are strict rules for filling them. Electrons will always fill in the lowest energy levels first, meaning they start with the shells closest to the nucleus. For the first 20 elements, the capacities are simple. The first shell holds a maximum of 2 electrons. The second shell holds 8. And the third shell also holds 8. Why does this matter? Because a full outer shell makes an atom completely stable. just like the noble gases in group 0 on the periodic table. But if an atom has an incomplete outer shell, it actively wants to react to fix that imbalance. We write out this structure using simple numbers. For example, sodium, whose atomic number is 11 and therefore whose electron count is 11, is written as 2.8.1. Let's walk through two worked examples. Nitrogen has an atomic number of 7, which means it has 7 electrons. 2 go into the first shell, leaving 5 for the second, so its electronic structure is 2,5, or 2.5 if you like. Magnesium has an atomic number of 12, that's 12 electrons, that is 2 in the first shell, 8 in the second, and 2 in the third. Its electronic structure is 2.8.2. Finally, let's review a few key elements from across the table to lock this in. Hydrogen, with just a single electron, is simply 1. Helium perfectly fills that first shell, so it is simply 2. Lithium has 3 electrons, forcing it to open a new shell. Its electronic structure is 2.1. Carbon is very important, of course. It has 6 electrons, so its electronic structure is 2.4. Neon has exactly 10 electrons, creating a perfectly stable structure of 2.8. And a larger element like calcium with 20 electrons stretches across 4 shells, written as 2.8.8.2. Let's now talk about the modern periodic table. There are roughly 100 known elements, 118 to be exact. They are arranged strictly by their increasing atomic number, which is, of course, their proton count. Because their chemical properties form repeating predictable patterns, we call it the periodic table. Picture the layout in your mind. The metals sit over on the bottom left, while the non-metals cluster on the top right, with a distinct dividing line between them. The vertical columns are known as groups, and the horizontal rows are called periods. Let's start with the columns. The group number tells you exactly how many electrons reside in the atom's outer shell. The only exception is group 0, where an element like helium has just 2. Because elements in the same group share that exact same outer electron count, they react in incredibly similar ways. This allows us to instantly predict their behavior. Take group 1, lithium, sodium, potassium, rubidium, cesium, and francium. They are all metals, and they all follow the exact same reaction playbook. However, there are clear trends within those columns. In group 1, reactivity actually increases as you move down the group, but over in group 7, it is the exact opposite. Reactivity decreases as you move down. Finally, let's look at the horizontal rows, the periods. The rule here is simple. Every time you drop down to a new period, you are adding another entirely full electron shell to the atom.